Hi, I'm Emre from Carnegie Mellon University, and in this talk I'll tell you about work that I did with Marijn Heule, where we show some separations in proof complexity. The systems that we will be concerned with in this talk are slightly unusual in that I don't expect you to have heard of them, but they're all meant to formalize a technique that I'm sure you're familiar with and have used informally when writing your mathematical proofs. So hopefully you'll find these proof systems interesting. The systems we will be separating in this talk are going to be built on top of resolution, which is arguably the simplest interesting system in propositional proof complexity and also the most widely studied one. So you may have at least heard of resolution, but just in case you haven't, here's what resolution does. It works with propositional formulas in conjunctive normal form, or CNF for short, which we view as a set of clauses, and resolution refutes such formulas by repeatedly applying the inference rule that you see here to derive new clauses, eventually deriving the empty clause. In this rule, A and B are clauses, and X is a variable. From the two clauses A or X, B or not X, this rule derives A or B. And this rule is sound. That is, any satisfying assignment to its premises also satisfies its conclusion. So if we can derive the empty clause from a set of clauses using this rule, then that set of clauses is unsatisfiable because the empty clause is just false. In this sense, resolution is a refutation system because it refutes the satisfiability of a CNF formula. Despite this, throughout this talk, I'll keep saying proof to stand for refutation because it's more conventional, and by a proof I will mean a proof of unsatisfiability, which we interpret to be the same thing as a refutation of satisfiability. Next, I'll show you an example of a resolution proof so that everything I just said is clear. Here's a formula, gamma, in CNF with 3 variables and 5 clauses. And for just this slide, I'm denoting negation by overlines like this to save some space. And this formula is unsatisfiable. And here's a proof in resolution. The inferences here are arranged in a tree-like manner. In this tree-like proof, each horizontal line is an application of the resolution rule, and the leaves are clauses from the original formula, and the root is the empty clause. As you see here, for instance, resolution allows us to derive z from these two clauses by cutting away the variable y, and so on until the empty clause is derived. It's not necessary to arrange the proof in this manner, and often we just write it out as a sequence of clauses, such that each clause is either a clause from the original formula or is derived from 2 previous clauses in the sequence using the resolution rule. Here I've grayed out the clauses that belong to the original formula, so there are just 5 clauses that were derived using resolution, with the final being the empty clause. And this is also a good time to talk about proof size, which we define as the number of clauses that you have in this sequence making up a resolution proof. So for instance, for this sequence-like proof, its size is just 10. And this matter of proof size is the primary concern of proof complexity. More specifically, we are interested, for a proof system P, in this quantity Sp of gamma, which is the size of a smallest P proof of the formula gamma. One of the goals of proof complexity is to relate different proof systems by this quantity. And here are 2 relations. For different systems P and Q, we say that P simulates Q if for all formulas, proofs in the system P are not too much larger than the proofs in Q. This is what the statement here says a bit more formally. And we say P is exponentially separated from Q if there's some infinite sequence of formulas admitting short proofs in P while requiring long proofs in Q. A lot of proof complexity relates different concrete systems to one another using these notions. And now, here's a list of some commonly studied concrete proof systems. The particular choice of the systems that I listed here is not really important, because the main point that I want to emphasize is that they're all capturing some version of a mode of mathematical reasoning. For instance, Frege is like the usual textbook-style propositional logical system. Extended Frege is a version where you're allowed to define some new variables to abbreviate expressions. Substitution Frege is another version where you're allowed to reinstantiate previously proved statements by renaming their variables, kind of similar to how you first prove a lemma and then use it several times in different contexts. Other systems correspond to geometric reasoning or algebraic reasoning, and so on. The bottom line is, all of these are motivated by some part of the mathematical practice. And the proof systems that we will focus on in this talk are going to be motivated in a similar manner. Specifically, they're motivated by the use of the following phrase, which, like I said at the beginning, I'm sure you've all written in some proof. You often use this phrase to simplify or shorten proofs, which makes it really natural to study from the perspective of proof complexity because we are interested in proof size. You may say, for instance, without loss of generality, assume x is greater than or equal to y when proving a result that is unchanged by swapping x and y, because the proof of the other case is essentially the same. Or maybe you're talking about graph coloring and you pick some vertex and assume it's colored red, because if it weren't, then you could just swap red with some other color in your proof. Or if you're proving some result about a random variable, you may assume for simplicity that it has expected value 0 when you can recover the more general case by translation. And there are plenty of such examples. So in this talk, we will focus on proof systems that capture this kind of reasoning at the level of CNF formulas. Note that really strong systems like extended Frege or substitution Frege can already simulate this kind of reasoning, but they can also do much more. And none of the other systems that I previously showed enable this kind of reasoning. So we will be looking at proof systems that are meant to capture the ability to reason without loss of generality without going overkill in terms of strength. And we will start with a really simple example of what we would like to be able to do, because the instances that I have on this slide are rather informal and a bit too general. So now I'll try to show an example of what it even means to derive clauses without loss of generality. For this example, let gamma be some formula in which the literal not x does not appear. And to be concrete and simple, let's say gamma has just a single clause, x or y. Now, without loss of generality, we may enlarge gamma with the clause x. And we need to justify this, just as you would do when making an assumption without loss of generality in your proofs. Here, the justification is that we're only trying to prove unsatisfiability, and adding x to gamma does not change its satisfiability status. In other words, gamma is satisfiable if and only if gamma n x is. This is because since x does not occur negatively in gamma, it cannot possibly hurt to assume that it is said to be true, which we achieve by adding the clause x to gamma. And here is an important thing to notice about this. The clause x is not necessarily logically implied by gamma. In the proof systems that I showed a few slides back, with the exceptions of extended and substitution Frege, you can only derive things that are logically implied. But in the current situation, x may not be implied, because there might be an assignment satisfying gamma without satisfying x. This does not mean that we are doing something unsound. And more generally, we will call a clause redundant if it can be added to a formula without affecting its satisfiability. And we will define proof systems that allow us to derive redundant clauses. We need to restrict our notion of redundancy though, because as it's written here, it is just a semantic property and we cannot necessarily check redundancy efficiently. But the whole point of proofs is that they should be easy to validate, so we will work with syntactic criteria that are sufficient but not necessary for redundancy. And we will use those criteria to define our inference rules. To keep things simple in a talk, I will actually define only the simplest redundancy criterion. The rest of them are various relaxations of the definition that we are now looking at, which is the notion of a block clause. Now, let P be a literal. We say that a clause C of the form P or C prime is blocked for P with respect to a formula gamma if for every clause D in gamma that contains not P, the results of applying the resolution rule to C and D, which gives the clause you see here, is tautological. Namely, it contains complementary literals. In case this was hard to parse, let's make it clearer with an example. In this example, C is blocked for X with respect to gamma. Let's check this carefully. Here, X plays the role of P in the definition, and the clause Y or not C plays the role of C prime. We need to look at the clauses in gamma that contain not X, and we can disregard the others. It is easy to see that for this first clause, the condition is satisfied, because resolving it with C over X gives Y or not C or not Y, where Y and not Y are complementary. And a similar thing is true for the second clause, because this time we get Y or not C or Z, so C is indeed blocked for X. And we call a clause blocked if it contains a literal that it is blocked for. The notion of a blocked clause was defined by Oliver Kuhlmann, and he showed that block clauses are redundant, so they can be used to define inference rules. And obviously we can efficiently check whether a clause is blocked or not, so we now have what we wanted. And before proceeding, notice the following about this definition. If not P does not occur anywhere in gamma, then C is automatically blocked. This means in particular that if P is a new variable relative to gamma, then C is blocked regardless of anything else. With that in mind, let's continue. We are now ready to talk about the inference rules. Here, just to be formal, I'm defining a proof like we saw at resolution, but in a more generic way. This time a proof is a sequence of clauses where each clause is either in the original formula or is derived from the set of all previous clauses according to some rule of the proof system at hand. The rules that we will have are the resolution rule, which you've already seen, the extension rule I mentioned earlier, which allows us to make definitions by introducing the three clauses that express this formula. Here we call X an extension variable, and it should be a new variable. That is, it should not occur in the original formula, or any of the previous clauses in the proof, or the right-hand side of the definition. So in particular, X is different from the variables of P and Q, which are arbitrary literals. And we finally have some redundancy rule, which allows us to derive a syntactically redundant clause with respect to the set of all the previous clauses occurring in the proof. With different choices of those inference rules, we obtain different proof systems. I'm writing R to denote the base system, which is resolution. ER is extended resolution, which has the resolution rule plus the extension rule. BC is the blocked clauses system, which has resolution plus the ability to add block clauses. And there's also this system that I denote by BC minus. If you recall, I mentioned that block clauses could include new variables, similar to extension. So this BC minus is the version of BC where we disallow new variables from appearing in the proof. And although I haven't explicitly told you about them, they're all the generalizations of block clauses which give rise to proof systems, and they can also be restricted in a similar manner to disallow new variables. This restriction is really significant because it turns out that without it, BC actually generalizes extended resolution, which we were trying to avoid in the first place because it is too powerful. So I claim that for those syntactic redundancy-based systems, the versions without new variables are much more interesting. This is because they are still strictly above resolution and allow us to reason without loss of generality, but they do not go all the way up to the strength of extended resolution. Our focus in this work is on those versions without new variables, because certain variants turn out to be quite interesting. Here are some results already known about those proof systems. These combinatorial principles, which require large proofs in many proof systems, all turn out to be easy for a modest generalization of BC minus, despite it having the same limited syntax as resolution and no new variables. Most of those upper bounds are due to Sambas and Neil Thappen, who also showed that lifting techniques cannot be used for proving lower bounds against that system. The lower bounds here are for different mild generalizations of BC minus. The first was proved by Oliver Kuhlmann and the second by Bass and Tappen. Here's another reason why those systems are interesting, which will also serve as a segue into our new results about them. In a really relaxed sense, BC, without new variables, simulates ER. Let's parse this lemma together. It was observed by Oliver Kuhlmann back in the paper where he defined block clauses. If we have a formula gamma with an ER proof of size m, then we can take this small CNF x consisting of two clauses that have some new variables and attach x to gamma so that the resulting formula has a proof of size linear in them. This is not an actual simulation because in BC- we are actually proving a different formula. It may seem like this result is not that interesting because we are essentially just incorporating new variables into the formula. But a similar idea allows us to construct some formulas to prove separations across the different generalizations of BC-. And the nice thing is, those proofs are completely modular, that is, we reuse the same construction for multiple separations, and we are also able to use previously known upper and lower bounds as complete black boxes. We've finally come to talk about the phrase that's in the title of our paper. I'll explain how to use what I call guarded extension variables to prove separations across different generalizations of BC-. We start with a formula with a short ER proof. Keep in mind the result from the previous slide, where we incorporated some new variables into the formula and made it easy also for BC-. To separate two systems, P and Q, that generalize BC-, we will incorporate extension variables in ways that are useful to only one of the two systems. We will achieve this by guarding the variables to make them hard to access. P will still be able to somehow use the included variables to end up with a short proof by simulating the ER proof. This is the upper bound. And Q will be completely unable to achieve any speedup despite there being some new variables present in the formula. And this is the lower bound part. In this way, we will use a separation between ER and Q to obtain a separation between P and Q. This is made possible by the fact that syntactic redundancy rules require some conditions to hold for every single clause in the formula. So we can guard the new variables by some evil clauses, which can only be overcome by some of the systems. Here's a simple example of what I mean using BC-. With respect to this formula, we know due to the definition of a block clause that any clause blocked for x has to include both not y and y, which makes any such clause useless for shortening a proof. By scaling up versions of this idea, we can impose some restrictions upon the set of redundant clauses derivable in each proof system that we have. Proving a separation then turns into a balancing act where we try to limit the abilities of one system while making sure not to constrain the other one too much. Let's look at a summary of the results we proved. Here you see some generalizations of BC-, and those three that are closest to it are its weakest generalizations in qualitatively different ways. The black arrows are relationships that are already known. The red ones are new in this work. The way to read this diagram is as follows. A solid arrow from P to Q, like this, means that P simulates Q. A dashed arrow from P to Q with a circle as the arrowhead, like this, means that P is separated from Q. And a solid arrow from P to Q with a gap in between, like this, means that P both simulates and is separated from Q, hence is strictly stronger. With variations on the recipe that I've described in the previous slides, we are able to prove a whole bunch of new separations. Also in ongoing work, we have the two missing relationships here determined conditionally, and we are now working on proving a lower bound against this SBC- system, to make those relationships unconditional and thus give a complete picture of the relationships between the systems on this triangle that are the closest to BC minus. And by the way, this SBC minus and SPR minus are the systems which have those strong upper bounds for the combinatorial principles that I showed earlier. Now, in the rest of the talk, I won't explicitly show the proofs of the separations, but I want to emphasize that they're relatively simple, at least compared to proving separations completely from scratch. And I will at least quickly show you what the separating constructions look like. In all of the constructions we are about to see, assume that gamma is some formula with a short ER proof of size m. This formula, f of gamma that you see here, separates this Rat minus system from the other two. The asterisk means that the separation is conditional, and the condition is that ER is separated from the weaker system. So we read this statement as unless SBC minus simulates ER, it does not simulate Rat minus. Now let's take a closer look at the formula. First of all, it contains gamma itself. It also contains m new variables, xi, such that xi and not xi appear in disjunctions with every clause of gamma. It turns out that this formula is easy for this Rat minus system, regardless of whether gamma is. And the other two get no speedups, despite the presence of the new variables here. This is another simpler one, where we now have two sets of new variables, xi and yi, and those clauses simply say xi if and only if yi. This time, Rat minus cannot make any use of the new variables, while the other two can. And this is a more complicated one, because this SBC minus system is able to do a lot of interesting things, so it is harder to work against. But still, this construction gives a conditional separation between those two systems, SBC minus and GUR minus. We are at the end. Thanks for making it this far, and let's conclude with some take-home messages. So what we did is give a recipe for proving separations between those unusual proof systems in quite a modular way. And by repeatedly using that recipe, we were able to give an almost complete picture of the weakest generalizations of this BC minus system. And if you're interested, here are some open questions that I'd like to see answered. I think the most pressing one is to prove some lower bounds against those two strong generalizations of BC minus. Like I said earlier, I'm working on a lower bound against the first one here, SBC minus. And another issue is that we have all those separations, but they use artificially constructed formulas. In proof complexity, people generally seek to prove separations using encodings of natural combinatorial principles because those tend to give you a more intuitive understanding of the relative capabilities of the proof systems. So it would be nice to reprove our results with more natural formulas. Also, as you might have already inferred, the study of those proof systems kind of lives on its own island right now, disconnected from the rest of proof complexity. Some things are known. For instance, we know that bounded depth Frege does not simulate BC minus due to an existing lower bound. But I think the converse direction is more interesting. For instance, is there any subsystem of Frege strictly about resolution that even a very strong variant of BC minus simulates? And finally, we have a generic recipe in this work. Although it uses some properties quite specific to the proof systems at hand, could it be maybe possible to somehow adapt the high-level idea for other uses in proof complexity? And that's it. Thanks again for listening. Also, since I gave no explicit references in the talk, here's a list of papers to look at if you're interested in previous work.